Hello there. Welcome back to A Slice of Physics. We have recently been talking about magnetic fields and currents a lot. We have seen that every current has a magnetic field. We have also seen that every magnetic field applies a force on a moving charge or a current. And in the last video, we saw how we can be clever about having a current loop in the presence of a magnetic field and pass a current through that loop to create a torque or a spinning motion, which is very, very useful in all kinds of applications involving electric motors. So now we are taking the next step in this discussion to see, well, if there's a lot of interactions between magnetic fields and currents, and if I can pass a current through a coil to make it spin, is there something I can do to induce a current in a coil in the presence of a magnetic field? So this is a situation where we are going to create a current in a wire, which again has lots of applications. You rely on it every day. You plug in things into the wall. All of that power comes from a power plant somewhere. And we're going to understand how those currents are created. And they all involve magnets or magnetic fields. In order to induce a current, you first got to induce a potential difference or EMF. So we're going to discuss the concept of a motional EMF. So we're going to see when and how we can induce a current in a coil. And we will understand this with a model of induced EMF, potential difference. And we will consider a whole bunch of things that we've been talking about: forces, speeds, electric fields, magnetic fields, potential difference, current, resistance, power. All right, and we'll bring a lot of this together in this video. Okay, we're going to start with talking about an important scientist, a British scientist called Michael Faraday. That name, even if you've never heard it before, will seem familiar to you because of the unit of capacitance. The unit of capacitance was farad, and that's named after Faraday. Faraday worked in the early to mid 19th century and did a lot of experiments with magnets and electric circuits. This was way before us understanding the structure of the atom and understanding that they're made of electrons and protons and all that, which is why the model of current is not consistent with the motion of electrons that we talked about before. But some of the experiments that Faraday did were he took a coil. We've talked about the current coil. So far, we talked about a current coil where it was connected to some kind of a battery and there was a current passed through it. But what Faraday did was he took a coil, no battery, connected an ammeter to it. So this is the device that lets you measure current. It lets you do two things. It lets you measure the magnitude of current. So the more the dial deflects, the more the current is. But it also lets you measure the direction of current. The way this needle deflects gives you an indication of direction of current in the circuit. So it gives you magnitude and direction of the current. So he took this, there was no battery, nothing, just a coil and an ammeter, and he placed a magnet inside the coil. And when he placed the magnet in the coil, let's say with the North Pole there and the South Pole here, nothing happened. But in the act of placing the magnet, he was moving the magnet into the coil, and surprisingly, when you moved the magnet in, so when the magnet is in motion in near the coil, moving in or moving out, there was a current. And if the magnet was moving into the coil, the current was in a certain direction. And if the magnet was moving out of the coil, the current was in the opposite direction. And the faster you moved the magnet, the more current you got. You will see some examples of this that I'll bring you in class and demonstrate. And you will also see some PhET simulation lab that you do where you see this for yourself. But the point is, a stationary magnet near or inside a coil produces no current. But a moving magnet into or out of the coil produces current in the coil. So this is a way we can generate current and then use it to power all of our devices. So instead of the ammeter, if you had a bulb in the circuit, the bulb would glow based on moving the magnet into or out of the coil. And as Faraday was continuing to do his experiments, if he left the magnet alone, left it stationary, and had a coil and moved the coil in or out of the magnet, the same thing happened. So moving the magnet or coil into or out of the coil or magnet, doesn't matter which one you moved, you would get a current. And then lastly, he took the same setup, placed the magnet very close to the coil, but just outside, let's say, so it's free to spin. And then he spun the magnet near the coil. And that also created a current. So spinning magnet near a coil induces a current in the coil. We will bring all of this together into something that's called Faraday's law of electromagnetism in the next video. But in this video, let's just talk about the basics of how this works, how moving something in the presence of a magnet induces a current. So to do this, I'm going to take a situation here where there is an external magnetic field, and let's say it goes into the screen, as shown here by these X's. Then you take a piece of rectangular metal and place it here, and then you do some work on this piece of metal by pulling it to one side. So let's say you pull it to one side at a constant speed v. So you're applying a force, and the net force somehow on this will become 0. We will see why that happens. So because the net force is 0, even though you're applying a force, it moves at a constant velocity v to the right. So this is a metal, and every piece of matter is made up of trillions upon trillions of charges. Metals are special in the fact that the electrons, the valence electrons, are free to move. They're not bound to atoms. So it's like you're moving trillions upon trillions of charges to the right. And you know that a magnetic field applies force on a moving charge. You can use your second right-hand rule to figure out how that works. So you place your thumb in the direction of motion. You place all of your fingers in the direction of magnetic field. So they will be this way, and they will all be pointing into the screen. And when you do that, your palm is facing up, which means the force on positive charges is going to be to the top, which also means that the force on negative charges is going to be to the bottom. So the negative charges are free to move, so they will all end up collecting at the bottom. That'll leave a deficiency of negative charges at the top, so you'll end up having a positive charge at this end. So let's write this down. By moving a metal in the presence of a magnetic field, I induces a dipole. So this metal becomes an induced dipole. And the separation of these charges creates a potential difference. So this now acts like a parallel plate capacitor, kinda, with positive charges on one end and negative charges on the other end. So the piece of metal, based on these separations of charges, ends up having electric field that points this way. So magnetic field is pointing into the screen, and the electric field is pointing from top to bottom in this case. And that also creates a potential difference across these two ends, which is simply the electric field times the distance. So let's call the length of this L. So the potential difference across the two ends of this metal will be E times L. Okay, so one interesting question is, how long will this charge separation continue to take place? Well, you see that the external force from the magnetic field causes negative charges to go down, but then you've got this electric field that is induced as a result of separation of charges, and that electric field will apply a force of its own on a charge. So if I've got a free charge over here, and let's just pretend that positive charges are free to move, even though that's not true, let's just work with our current model. So if I have a positive charge that is sitting here in the middle that's free to move, it experiences two forces. I'm going to show that outside here so it doesn't get too crowded. So the free positive charge experiences two forces. It experiences a force from the magnetic field that is to the top based on the fact that it is moving in this direction. And once the charges get separated and it becomes an induced dipole, it experiences a force from the electric field that is to the bottom in the same direction as the electric field. And the separation of charges will take place until you reach equilibrium, and equilibrium will be defined by these two forces, F magnetic and F electric, being equal to each other, so that the charge that's free to move, that's sitting in the middle, is happy to be sitting in the middle because it's now in equilibrium based on the two forces. All right, let's now put this together with some equations. So we know what F magnetic is. It is Q times V times B. times sine of alpha. In this case, alpha is 90 degrees. These charges are moving left to right. The magnetic field points into the page. The angle between them is 90 degrees. So I don't need to write that term. Sine of 90 is just simply 1. F electric will be Q times E. You remember that force on a charge from an electric field is simply that charge times the electric field. And so for equilibrium, these two forces have to equal each other. Magnetic force equals electric force. They are in opposite directions. So I can set that QVB equals QE. Q cancels from both the sides, and I get an equation that simply says electric field after equilibrium is reached will be equal to the speed times the magnetic field. So the electric field is the induced electric field from the separation of charges. Magnetic field is the external magnetic field. V is the speed with which I move the strip. And you get this relationship after equilibrium is reached. Which then, thinking of this as a parallel plate capacitor, the electric field inside the metal is uniform. So then in that situation, you remember that delta V was simply E times X, where X was the distance between the two plates or two separation of charges. So in this case, that distance is L, the length of this strip. So this would be E times L. So delta V would be V times L times B. So this delta V is called the induced EMF. EMF is the term for potential difference. Let's be sure here, this delta V is capital, that's potential. This little v, so this little v is speed, and this capital V is potential. And so delta V is potential difference, which is related to the speed times the length of the strip times the external magnetic field. So let me recreate that over here. And so I've got that metal strip that I'm moving to the right with the speed v. It results in a separation of charges where the top end becomes positive, the bottom end becomes negative. So now, as long as I keep moving this separation of charges will reach that equilibrium point. And so this now starts to look like a battery. So I can even put a little cap here to remind you that this is like creating a potential difference. In a battery, we do it with chemical energy. Here we're doing it with the external magnetic field and the work that we're doing on this strip by moving it to the right. But essentially, we have kind of like created a battery. So then if I have the rest of the circuit, I could have a wire that's stationary. So let's say this battery has little pieces that are sticking out, and it sits on a rail, a stationary rail of wire that lies like this. So as I drag this to the right, the circuit is complete. There is a potential difference. So there is going to be a current in the circuit from the positive end to the negative end. So using the current model, we've got a current in this direction. So all I have done here is gone from induced EMF, which is the potential difference because of the separation of charges, to induced current by completing the circuit. So this current goes in this counterclockwise direction, and inside this metal, to complete this direction of current, the current will go from bottom to top. And we know that there is a force from an external magnetic field on a current, so we can see what that would be. So in this case, the current is going up. So my thumb will point up. My fingers will point into the page, so they will be oriented below the thumb like this. And when you do this with your right hand, your palm is over here, which means the force on this current strip is going to be to the left. So I'm applying an external force to move it. So this is my force, let's say external, from my hand to move it to the right. And then as a result of the induced EMF and completing the circuit, there's a current flow, and there's a force from the external magnetic field on that current that acts to the left. So let's call this F magnetic. So this is what I was referring to as you can move it at a constant V, because even though you're applying a force to the right, when you complete that circuit, there is going to be a force to the left from the external magnetic field on the current. And so those two forces can equal each other, and you can move it at a constant speed. So let's see what these forces would be. We know that the F magnetic would be I times L times B, and the F pull has to be equal to F magnetic in order to have a constant V. So the F pull will also be equal to I times L times B. And from the previous slide, we had an expression for delta V was equal to V times L times B. So using Ohm's law, I have the current as delta V over R, which would be VLB over R, where R is the resistance of the circuit. So by plugging that in, I will get, instead of I can write VLB over R times L times B. So this gives me an expression for the pulling force as well as the magnetic force to be equal to V times L squared times B squared over R. Lastly, looking at the energy considerations in this situation, I have delta U, the potential energy, is equal to the work done from external force. So that would be equal to the F pull times delta X. And if I divide both sides by delta T, I will get power input. So this would be power input of how much power potential energy I'm putting in per second. That'll be equal to F pull times delta X over delta T, which, by the way, you know that is just V, the speed. So this becomes F pull times V. So we had an expression here for F pull as V times L squared B squared over R. So this simply becomes V squared L squared B squared over R. You might be getting confused with too many terms here, but just look at it at a high level and see what it really means. There is a punchline that we're getting to here. So lastly, there is a power that's also dissipated. So let's call that power dissipated. And in any circuit, we know that that's equal to I squared times R. And I here was VLB over R. So this simply becomes V squared L squared B squared over R squared. That's all I squared. And then I multiplied by R. One of these R's will cancel, and you see that you get the same expression. So the key here is, when we talk about moving this to the right and producing a current, there might be a notion of we are creating energy out of thin air. And this shows us that that's not true. There is no free energy we're creating. We're creating energy in the electrical sense by putting in work in the mechanical sense. So we're exchanging one form of energy for another, and the rate of creation of energy by creating the current using our external work equals the rate at which we dissipate energy from that current flowing through a resistance. So total energy is conserved, and there's no real magic here. It's just being clever about using one form of energy to get another form of energy that we are after. So in this video, we saw how we can induce current, which comes from the motional EMF. We looked at Faraday's observations of the induced current. We saw that moving a conductor in the presence of an external magnetic field creates a separation of charges, which results in a potential difference or induced EMF, which then, if I complete the circuit, it can facilitate a current that's called induced current. And we saw that the energy and power considerations of this are consistent with energy conservation. Thank you.